Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Welcome to the CSE Colloquium. Our speaker today is Mark Zhandry from Stanford University, and he'll be talking about modern cryptography, and he has done a lot of work on taking modern cryptography and making it safe for a quantum world, but he's going to talk about some other surprising results on the power of modern cryptography. Thanks.
Right. Thank you. All right, so let's begin with an extremely brief history lesson on cryptography. So in cryptography, about 40 years ago, is really what I consider the beginning of modern cryptography. And this is where we laid a lot of the foundational work for cryptography today. We figured out how to do things like public key encryption, where two parties don't need to meet in person before they actually engage in a protocol, and other things like digital signatures. After the foundational work in the 70s and 80s was sort of the Wild West of cryptography. We were figuring out how to do lots more cool things, like proving that we know something without actually revealing what it is we know, doing computation amongst a bunch of parties to figure out some function of their input without actually revealing each party's individual input, and other things like digital cache. I think now we are really in the golden age of cryptography, where we really know how to do a surprising number of applications of cryptography. Some of the things that have been discovered in just the last few years include computing on encrypted data and hiding secrets in code. And it's a big question what the future will bring. I think the future in cryptography is going to be a very exciting place. So one of my goals as a cryptographer is to continue pushing the frontiers of what is possible with cryptography and develop new cutting-edge cryptographic applications. But while these cutting-edge applications are really interesting, they have one major limitation. So if we sort of group all the cutting-edge applications together, they're going to be on this one side of the cryptographic landscape. But what is actually usable, practical, and actually implemented today is completely on the other side and more or less coincides with the foundational work from 30, 40 years ago. And there's really quite a large divide between the practical applications and the cutting-edge applications that are going on today. So another one of my research goals is to try to take these cutting-edge applications and bring them in, bring them closer to practice with the hopes that someday they'll actually be practical and used. All right, to motivate my work, I'm going to talk about a problem that is particularly interesting to me. And this is the problem of exchanging keys over a public channel. So the general problem is as follows. We have Alice and Bob, and they want to establish a shared secret key between the two of them so that they can later on encrypt their messages and send them back and forth. But we live in a digital age, and they're maybe on different continents. They're never going to meet in person. The only way they can communicate is over a public channel that everyone else in the world is listening to. So the question is, how can they engage in a protocol such that they establish a shared secret key, but an adversary who's potentially eavesdropping and learning all of the messages sent back and forth, we don't want him to learn anything. All right. So this problem was first solved by the famed Diffie-Hellman protocol back in the 70s. So in the Diffie-Hellman protocol, it's actually very simple. The two parties generate some secret key individually, generate some user secret, and then they derive some public value from that secret that they send to each other. Now, after they've done this, Alice knows her secret, Bob's public value. Bob knows Alice's public value and his own secret. So they know different things, but somehow in the protocol, they're magically able to figure out a shared key between the two of them. Now, meanwhile, the adversary, he doesn't get to see either of the public values either the private values generated by the parties, all he gets to see is the public values that they exchange. And just given the public values, he cannot figure out the secret key. So this is generally what the Diffie-Hellman protocol looks like. And this structure is what we actually call a non-interactive protocol. So in a non-interactive protocol, there's just a single round of messages that happen simultaneously. It's not like Alice needs to send a message to Bob, then Bob replies with some other message and so forth. All they do is just this one simultaneous message sent to each other. And non-interactive protocols have a couple key advantages over interactive protocols, which makes them very desirable. One is that they can be run offline in a practical sense. So today, a lot of our communication, rather than just point-to-point, is done over public forums like, say, Facebook. And in this setting, maybe not all the parties are logged into Facebook all the time. Alice lives in the US, Bob lives in Europe. They're in completely different time zones. They're never online at the same time. But that's actually not so bad. So Alice can run her half of the protocol when she's online. She can go offline, it doesn't matter. And Bob can run his half of the protocol later when he goes online. And at this point, the protocol is complete, so Bob can learn the shared secret key. And whenever Alice comes back online, she can read Bob's message and learn the shared secret key as well. And the point is that if you had an interactive protocol, where first Alice had to send a message, then Bob, and so forth, really it's going to take a long time for all the parties to have logged in enough times to actually carry out the protocol between the two of them. Okay, the other advantage, and I think this one is even more key, is that the protocol is reusable. So suppose Alice and Bob have run the protocol and established their shared key between the two of them. Now Charlie comes along and he wants to communicate with Alice and establish a shared secret key with her. Well, you might ask, okay, do we need to run the protocol from scratch again? And the answer is no. Alice has actually already completed her half of the protocol. She's already generated her secret key and published her corresponding public key. So all that's left to do is for Charlie to run his half of the protocol, generating his own secret key and public key, posting that to his public profile. And now Alice and Bob can read off the public values, use their own secret, and generate a shared key. We didn't need to rerun the protocol from scratch. And similarly, Bob and Charlie, now they've actually already completed the protocol. There's nothing more to do. They can just read off each other's public values and get a shared key just for the two of them. So in general, if you have n parties and they're all pairwise generating shared secrets between them, there's an order of n squared shared secret keys that you'll want to generate. But with this non-interactive protocol, there's only n messages ever being sent. Only the public key for every party is being published. And this is quite different from an interactive protocol where the protocol would need to be rerun from scratch every single time, and you would end up having n squared messages. Okay, so this is non-interactive key exchange. What I'm going to be talking about today is a very natural generalization to the multi-party setting. So now imagine you have a bunch of Facebook users and they've gotten together and formed a group, Facebook group. And now they want to send messages between each other over a public channel. Well, what they want to do first is establish a shared key that's shared among the whole group. So in this case, we have 4 people part of the group. We want them to each generate their own secret value, publish some corresponding public key, and now just based on the public values and their own individual secrets, we want them to be able to all learn a shared secret key among the whole group, but we want an eavesdropper who's only seeing the public values posted to the individual's profiles. We don't want him to learn anything about the key. Okay. All right, so what are some possible strategies for solving this problem? Well, we can actually solve this multi-party key exchange problem using stuff that's been around for 40 years. For example, using public key encryption, you can develop a protocol to solve this. Unfortunately, the resulting protocol is going to be interactive. We don't know, using standard techniques, how to achieve a non-interactive protocol. So this means the resulting protocol is all the parties must be online at the same time to generate the key. And this becomes very impractical for large groups of people. If you have thousands of people and you need them all online at the same time, you can imagine that that's a very difficult task. And then also there's this issue that it's only one time. For every single Facebook group, you're going to need to run the protocol. Whereas if you had a non-interactive protocol, every individual just runs it once, and suddenly all the groups now can establish shared keys without any additional interaction. Okay, so using the standard techniques from 40 years ago, probably not what we want. It turns out that a recent tool developed just in the last few years claims to solve this problem. And that tool is called multilinear maps. So let me just describe briefly what cryptographic multilinear maps are. So in a cryptographic multilinear map, there's two groups, G and GT. They're cyclic groups, which means that they're of the form some identity element, an element G, G squared, G cubed, and so forth. And eventually this wraps around, and you've raised to a high enough power, you get back to the identity element. So we have two of these groups, a source group and a target group. And we have some pairing operation that moves between them. And the pairing operation takes in n copies for some predefined integer n, takes in n copies of the source group, and outputs an element in the target group, satisfying this homomorphic operation. More or less, if you run the pairing operation on the bunch of elements, all the exponents come out of the pairing operation. And it turns out that these multilinear maps have a ton of applications, even in the case for n equals 2. This cryptographic multilinear maps were discovered around the year 2000, and they have been instrumental in solving many open problems in cryptography. Example being identity-based encryption, and actually the three-party version of the non-interactive key exchange problem. It wasn't until just 3 years ago that we saw the first candidate construction of a multilinear map for general n greater than 2. And using these multilinear maps, we can get a very simple protocol for multi-party key exchange in the general multi-user setting. And it can be used, and these multilinear maps can be used for developing many more cryptographic applications. Unfortunately, there's a really big limitation in using these multilinear maps to build non-interactive key exchange. And that is that the resulting protocol doesn't quite match the desired format that we wanted. Instead, what actually has to happen is before all the users run their part of the protocol, some central authority, say Facebook, has to generate some parameters for the protocol. So Facebook generates these parameters and publishes them, say, on the Facebook homepage. And now all the parties run the protocol just as before. So this slight modification doesn't necessarily hurt the reusability aspect and the offline aspect of non-interactive key exchange. But what it does is it places Facebook in a unique position where, because Facebook generated these parameters, it actually knows a trap door that allows them to totally break the protocol. So Facebook actually will, using these multilinear maps, Facebook will actually learn the shared group key. And this is really undesirable. If the Snowden leaks taught us anything, it's that we can't trust these big organizations to hide things from snooping three-letter government agencies. So what we really want is not a protocol with trusted setup like this one, but a protocol where Facebook doesn't play any role in the protocol except hosting the messages. All it is a public bulletin board for people to post their messages. It doesn't generate any parameters, and it's not involved in the protocol in any way. And in this case, Facebook is more or less just another eavesdropper on the system and shouldn't be able to learn anything. Okay, so multilinear maps, they don't seem like they really solve this problem, at least not satisfactorily. And this actually really bothered me when I first read about multilinear maps, and I made it my mission to try to figure out how to fix this and remove the trusted setup. I was initially trying things like trying to tweak the protocol to remove the setup phase, and I wasn't really successful. But then I stumbled upon this new tool called obfuscation, and I was able to solve this problem using this tool. All right, so what is obfuscation? So the idea in obfuscation is that you want to take a program and scramble it in some way such that you're not actually changing the input-output behavior of the program, but that the code of the program, the code of the obfuscated program that you output, doesn't reveal anything of the inner workings of the original program. So specifically, an obfuscator is a procedure that takes as input a program, outputs another program, with the functionality requirement that the output program behaves exactly the same. Same input gives you the same output. We also have some efficiency requirement where the obfuscator itself is efficient and the output program is efficient for some definition of efficient. And ideally, the security of the obfuscator would say that given the code for the obfuscated program, you learn nothing about the original program except the input outputs, which of course you can learn just by running the code on inputs of your choice. So the first candidate obfuscator was constructed just 2 years ago, and now I will show how we can use obfuscation to build multi-party key exchange without trusted setup. So I'm actually first going to describe a protocol with setup, so it seems like we're not really making progress. But then I'll show that our protocol has a very specific feature that allows us to remove setup entirely. The building blocks are the following. First, we're going to need a one-way function. This is the most basic object in cryptography. Oh, question?
Can you go back just one slide and just say a sentence about what does reveals nothing about formally?
All right, so the question was, what do I mean in this quotes reveals nothing about? It turns out that there's actually a little bit of a definitional problem in defining obfuscation. There's a way to formalize this that says if you have an adversary that learns some piece of information about the original program, then there must exist another adversary that learns the same piece of information only given Oracle access to the program, doesn't get to see the code. But it turns out that that definition is too strong and it's actually provably unachievable. And so we use a weaker notion which just says that if I have two programs that have the same functionality and I obfuscate them, I can't tell which one I obfuscated. Does that answer your question? Okay, so our building blocks, again, the first building block is a one-way function. It's basically the simplest object in cryptography. It's just a function that's easy to compute but hard to invert. We're also going to need a pseudorandom function, and this is a keyed function that in some sense looks like a random function if you don't know the key. And you can just think of a pseudorandom function as AES, where the key is just the AES key. In addition to pseudorandom functions, we're also going to need an obfuscator. All right, so the protocol is actually pretty simple. The parties each choose a random input to the one-way function and publish the corresponding output as their public key. Now, to actually allow computing a shared secret, Facebook, which is our trusted setup for now, is going to generate a key for the PRF, or AES, if you will. And the shared key for the group is going to be defined as the PRF using Facebook's key evaluated on the sequence of public keys of the parties involved in the protocol. Now, at this point, it's really unclear how to actually make this work because as it is, only Facebook can learn the shared group key. None of the other people can because they don't have the PRF key. But if Facebook just published the PRF key, then not only can all of the honest parties generate the shared key, so can an eavesdropper, because he would get to see the key as well. So this is where obfuscation comes in to help us. So what we do is have Facebook take their key and embed it in a program. The program works as follows. It takes as input a sequence of outputs of the one-way function. These are the y's, as well as an input to the one-way function and an index. The first step is it uses the index to select one of the one-way function outputs, and then it just checks that the provided input is actually the correct input to the one-way function that produces that output. If this check fails, if the input is actually incorrect, it just outputs some special symbol bottom and aborts. Otherwise, if this check passes, then it evaluates the PRF using the embedded secret key K on the sequence of input values. And this is the program that we're going to obfuscate. So intuitively, all the honest parties, they're trying to learn the PRF evaluated the sequence of public values. So they will feed in the public values as the y's. And then all of them know one of the pre-images, because that's how they generated them. So they'll be able to feed in the other inputs that cause the program to actually output the shared group key. Whereas an eavesdropper, all the eavesdropper gets is the public values themselves. He doesn't know what inputs to feed in the program to have it output the right thing. All right, so the setup protocol, basically Facebook just generates this program and publishes it, and now we're pretty much done. All the honest parties can run the program on the public values and their own individual input, their secret key, and then get the shared group key. All right, so it remains, a couple things remain. One, we need to prove security. So as I mentioned before, we're going to use this notion of indistinguishability obfuscation. But unfortunately, it turns out that indistinguishability obfuscation isn't enough for the protocol I just described, and we need to tweak the scheme a little. For one, we're going to have to replace this one-way function with something slightly stronger, a pseudorandom generator. So pseudorandom generator is a one-way function with a couple added properties. One, it's expanding. So it takes in, say, 128-bit inputs and produces 256-bit outputs. So given that it's expanding, most of the points in the codomain will not have pre-images, right? Because there's only a total of 2 to, if the size of the inputs are 128 bits, there's only a total of 2 to the 128 outputs. But the whole codomain is 256 bits, so there's many more possibilities. So the other requirement is that even though it's expanding and the set of image points is very sparse, we still want that a random output is computationally indistinguishable from a truly random string. All right, the other change we're going to need to make is we're going to need to replace our PRF with something a little stronger. And I won't go into what this means, but we're going to need it to be a puncturable PRF. And while AES, for example, does not satisfy this notion, we know how to build these puncturable PRFs from pseudorandom generators. And we know how to build pseudorandom generators from one-way functions. So from a foundational perspective, we're not really increasing the assumptions that we need for this protocol. And with these in place, we can prove security. OK, so that's our security statement. Now I want to show how to remove setup from this protocol. And the crucial observation is that the user messages and the obfuscated program that Facebook produces, they're completely independent of one another. The obfuscated program has no mention of the user's secret keys or public keys. And the user's secret keys and public keys are just inputs and outputs of a one-way function. They don't mention this obfuscated program in any way. And what this means is that the two phases, the setup phase and the user messages, can actually be run simultaneously. This is quite different from the multilinear map protocol, because there, the setup had to happen strictly before the rest of the protocol was carried out. All right, so our solution then is to designate one of the parties, say Alice, as a master party. And she's going to play the role of both herself in the protocol and as a trusted setup instead of Facebook. So she is going to actually be responsible for generating this obfuscated program and publishing it. So two things to notice. One, because this happens simultaneously, Alice just needs to still send one message. Just the obfuscated program and her public key together as one message. So it's still non-interactive. And then the other thing to notice is now Facebook, all Facebook sees is everyone's public messages. It doesn't play any special role. So from a security perspective, it's identical to Facebook is no better off than an eavesdropper on the system. And from a functionality perspective, everyone can compute their shared key as before just by running the obfuscated program on the public keys. All right, and that's the protocol for key exchange from obfuscation. We also investigate some stronger security notions. So remember, one of the advantages of a non-interactive protocol was that it's reusable. But so far, our security model has only considered a single set of users that get together and establish a shared key. So what happens in the multi-party setting? Well, it might be that on Facebook, there's a billion users, and various subsets of them are going to be joining groups, and these groups might even be overlapping considerably. The other thing is that an adversary can easily go and create his own users and have them join groups that are partially overlapping. So now we have this adversary. He's now playing a very active role in the security model. And yet what we want is that in any group that does not have an adversary in it still has secret keys that the adversary doesn't know. For the particular protocol, this more interactive setting brings up a very important question: who plays the role of the master party? For example, in the Alice, Bob, Charlie case, Alice can be the master party and everything's fine. But then what happens when Donald, Eve, and Fiona want to get together and establish a key? Alice isn't a part of that protocol. They can't use Alice's public program, or else if they did, Alice would learn their group key. So the takeaway is that every individual, we don't know which groups are going to be getting together and establishing keys, so every individual needs to be ready to play the role of a master party. And this brings up a really interesting problem with our protocol, and that is that the adversary is now sometimes going to be the master party. And this is where things go really, really bad. Because if the adversary is a master party in one version of the protocol, we actually can show that with our protocol, he can learn all of the user secrets and then break any other key that those parties generate. Okay, so we need to fix this, and we show that by tweaking the scheme a little, we can actually attain some form of security notion in this setting. And then in a follow-up work, we actually obtain the full adaptive security notion, but it uses some heuristics in order to argue security. And so it's actually a very interesting open problem to see if we can get the full adaptive security that you would want without using any of these heuristics. All right, so back to our picture of possible strategies. We had the public key encryption protocol, which was interactive, and we didn't like that. We have the protocol for multilinear maps, which required a trusted setup. But now we have this obfuscation protocol, which seems to solve all the problems. But unfortunately, things go wrong when you try to actually implement this. So the problem is that our obfuscators are actually quite inefficient currently. And constructing them involves many steps that are all computationally inefficient. So they roughly go as follows. The first step is to take the program and translate it into what's called a branching program or a matrix branching program. And this is basically this enormous sequence of matrices that various subset products correspond to outputs of the program. And the expansion in this step is truly enormous for most programs that you would want to obfuscate. The next step, we actually use multilinear maps. We, in some way, encode this sequence of matrices in the multilinear map. And then there are even more additional costly steps involving fully homomorphic encryption, which itself is a very expensive primitive. And even though there's been progress on making these things more practical, for example, I have some work showing how to improve the first step, the state of the art is still really impractical. So like, if I wanted to go out and try to implement this thing, it's hopeless, at least for now. Maybe somewhere down the line, obfuscation will become efficient, but for the foreseeable future, it's going to remain pretty impractical. So what I want to do then is somehow remove obfuscation. I want to obtain a simpler protocol that does not go through all of the heavy lifting in obfuscation, and that's what I will show now. Okay, so the observation that we can make is that we don't really need the full power of obfuscation. We're only obfuscating a very, very simple type of program. And it's basically, we're using obfuscation as a sort of access control mechanism. So what we can do is partition what the values we feed into the program into two parts. One I'll just call the inputs, and these are the y's, which will be the public values that are fed in. And the other is what I'll call the token. And this is the preimage that every party feeds in. The first step of the program is some validation step that checks a relation between the input and the token. And if this validation step passes, and only if it passes, the program will output a PRF evaluated on the input. So we see that all we really care about is that we're using obfuscation as sort of this access control where you can only learn an output if you're given the appropriate token. And this leads me to define a new primitive that captures exactly this functionality. And that's what I'll call Witness PRFs. So in Witness PRFs, there is some NP language, L, that everyone knows. And let's say Bob has an instance that's in the language, and moreover, he actually knows a witness to this fact. Alice, not knowing the witness, is going to generate two keys. One key is going to be what I'll call a function key, but it's basically just a key for a PRF. So it defines some PRF. And what's interesting about this PRF is that the domain for the PRF is actually instances. The other key is going to be public, and this is an evaluation key, which she can send to Bob. And Bob, with this evaluation key, runs some procedure on the key, his instance, and his witness, and he's able to learn the value of the PRF at the instance, assuming the witness is correct. So again, there's two modes here. There's two keys. One is a function key that allows you to evaluate the PRF everywhere. One is a function key that allows you to evaluate the PRF everywhere, and the other one is this evaluation key that only allows you to evaluate the PRF if you know a valid witness for that instance. In traditional PRFs, it's sort of all or nothing. There's only the function key. You can only either evaluate it everywhere or not. Here we have this public component as well. And for security, we require that if the instance is actually not in the language at all, in which case there is no witness, then even knowing the evaluation key, you can't learn anything about the output of the PRF on that instance. And we might ask that this even holds if X is chosen adversarially, and maybe even if the adversary has an oracle to the PRF function. Just want to point out that we don't actually make any requirements in the case where X is in the language, but the adversary doesn't know a witness. We only sort of handle the case where the instance is not in the language. All right, so now let's see how to use Witness PRFs to replace obfuscation. Basically, instead of an obfuscated program, the master party is just going to generate keys for the Witness PRF and publish the evaluation key in place of an obfuscated program. And the shared secret for all the parties is just going to be the PRF defined by the master party's secret key evaluated on the public keys of all the users. Okay, so the question is, how do we actually make this work? What is the right language to use to allow all the parties to learn the shared key? Well, all the parties, they only have the evaluation key for the PRF. So the only way they can learn the output is if they know a witness. So they all need a witness that the sequence of public keys is in the language. In particular, this means the sequence of public keys is in the language. And then also we need that a witness is hard to compute given the instance, because the instance is public. If it was easy to compute a witness, then so could the adversary, and then security is lost. So the language we define is actually sort of the natural one. It's basically the languages of outputs of the one-way function such that at least one of them has a preimage. And because everyone generated their component by evaluating the function on an input, they all know the input, so they all know a witness for this language. Meanwhile, an adversary, he only gets to see the instance itself, and the one-wayness of the function says that he can't compute a witness. All right, so with everyone's witness, they can all compute the shared secret key. And we have a security theorem saying that the protocol is secure. Just like in the obfuscation case, we're going to need to assume that the function f is actually a pseudorandom generator.
So doesn't Alice have access to the key fk? Couldn't she evaluate it everywhere?
Yeah, so the question is about Alice. Alice generated the secret function key. She knows it. So yeah, she could actually generate this directly without her witness, but the rest of the parties don't. So the rest of the parties actually will need to use the evaluation key with a witness. Yeah. Okay, so now I actually am going to prove this theorem to you. Okay, so the adversary, in order to prove security, we want to see what the adversary sees and what he's trying to learn and show that that can't actually happen. So the adversary sees the sequence of public keys, and they're just generated as outputs of the function f on random inputs. The adversary also sees the evaluation key for the witness PRF, defined for the language L that I've reproduced above. All right, and his goal is to learn the PRF value for the witness PRF evaluated on the sequence of public keys. And we want to show that basically the adversary can't achieve in his goal. All right, so the first step was very common in cryptography, and we're actually going to define an alternate world where we change what the adversary sees. So in this world, the evaluation key, this is the same as before, but now the public keys are actually generated as just truly random strings. They're not the outputs of f on random inputs, they're just truly random. But as we said, we're assuming f is a pseudorandom generator, and so this change is indistinguishable to the adversary. That's exactly the security of a pseudorandom generator. A random output is indistinguishable from a truly random string. All right, so if the adversary succeeded in the real world, he's also going to succeed in this alternate imaginary world. But in this imaginary world, something interesting happens. Remember that our pseudorandom generator was expanding. And it was actually quite expanding. It say doubled the length of the input. And what this means is with high probability, a bunch of random strings drawn in the codomain of the generator don't have any preimages. All right, so if we think of this whole space here, y, as the output space of the generator, there's 2 to the 256 possibilities here. But the set of image points is much smaller, right? The inputs to the function are only 128 bits, so there's only 2 to the 128 possible images. So as we're generating these random strings in the whole codomain, they're most likely never going to hit an image point. And so they won't have none of these will have a preimage. And by the definition of our language, this means that these public keys will actually not be in the language at all. And now we're essentially done. So remember, the adversary's goal is to learn the PRF value on these points. And we said that success in the real world implies success in this alternate world. But in the alternate world, the adversary only sees the evaluation key, and yet is trying to learn the PRF evaluate on a point that's not in the language. But the security of the witness PRF says that this goal is hopeless, and so we're done. We've just proved that the adversary can't succeed in his task. So now the obvious question is, how do we build these witness PRFs? And now I'll roughly describe how we go about building them. So first, what we're going to do is we're actually going to construct witness PRFs for a limited class of languages. And this class of languages is derived from the subset sum problem. So just as a bit of notation, for an integer vector A, I'm going to define subsums as the set of subset sums of the elements in A. So just pick some subset of the n elements, sum them together. That guy is going to be in the set. We can rephrase the subset sum problem in terms of this subsums operator as follows. Given some sequence of integers and some target integer t, determine if t is actually in the subset sum space of that sequence of integers. All right, so just some pictures to describe the subsums set. So what we're going to do now is I'm going to build a witness PRF for just sets that can be represented as subsums of some integer vector. All right, so how do we do this? I won't describe exactly how this works, but we're going to build them from multilinear maps. And the first step of the generation procedure is to come up with two encoding functions. One is what I'll call a source group encoding function, enc, that maps integers into group elements in the source group of the multilinear map. And the other one is a target group encoding function that maps integers to target group elements. And we're going to build these encoding functions in such a way as to exploit the homomorphism property of the multilinear maps so that they satisfy this following property. So if I take a bunch of integers and I map them using the source group encoding function into source group elements and apply the multilinear pairing operation to them, I will get some target group element. And what I want is for this target group element to be the same exact element that I get by first summing up the integers and applying the target group encoding function. All right, so this is sort of the property we want to these encoding functions, and we show how to build these. And now the secret function key for the witness PRF is just going to be the target group encoding function. And the evaluation key is going to be the result of applying the source group encoding function to all of the integers in the vector A. And we're also going to need a source group encoding of 0. OK, so now I'm going to actually define the witness PRF. So the witness PRF, remember, the instances are just integers. So what we're going to do is take an integer t and just map it to a target group element using the target group encoding function. And that's how the PRF is defined. Now, the eval procedure, we want to be able to reconstruct this t value, this encoded t value, without the function key at all, but only given a witness and the evaluation key. So remember that the evaluation key is this sequence of encodings of the values of the vector plus an encoding of 0. So what the evaluation procedure is going to do is it's going to use the witness to select the appropriate subset of the encodings. And for every encoding that wasn't selected, it's just going to replace with 0. And now it's going to feed this guy, all these, into the multilinear pairing operation. And the homomorphic property that we had on the last slide guarantees that if W is a valid witness, I get exactly the same encoding of T as I would have by encoding it directly. OK, so from a functionality perspective, this works. There are some final pieces. One is to actually argue security. And roughly, security follows from the following argument, that if T is not in the subset sum space of A, it means there's no subset of the integers in A that sums to T. which means this translates to there being no subset of the elements in the evaluation key that, when paired together, form this encoding of T. There's some details here. We need to prevent the adversary, say, from including A1 3 times or something like that, but those can all be handled relatively easily. And we get a complexity assumption on multilinear maps that says that this encoding of T actually is uncomputable to the adversary if there is no witness. All right, and then the final piece of the puzzle is actually taking this limited purpose witness PRF and boosting it to a full-fledged witness PRF for any NP language. And we do this by giving a new reduction from any NP language to the subset sum problem. And the reason we need to give a new reduction is that we need the reduction to satisfy a particular property. And that is that the set of integers A cannot depend on the instance. And this is because it's part of the input to the witness PRF generation procedure. And when you're generating, you don't know the instance yet. So we really need the vector of integers A to only depend on the language itself and not the instance in the reduction. T, on the other hand, will depend on the actual instance. So using this new reduction, we're actually able to take our witness PRF for subset sums and get a witness PRF for any language that you want in NP. All right, so now I want to just compare our three protocols that we've discussed, just to see if we've made any progress in terms of efficiency. So all these protocols, it turns out that we implement them ultimately on this new tool, multilinear maps. And so a very convenient way to compare them is to look at the level of multilinearity required, the number of inputs to the multilinear pairing operation. And the reason that this is sort of a useful proxy for efficiency is that the dominating factor in terms of the inefficiency of multilinear maps is determined mostly by the multilinearity required. So in the basic protocol, the level of multilinearity is just the number of users minus 1. It uses the multilinearity actually very effectively. But as we discussed, it has this trusted setup, and so it is rather undesirable. For obfuscation, it turns out that no one's actually worked out exactly how inefficient obfuscators are. So the general form of the multilinearity required is going to be the number of users times some security parameter that comes from the PRF and the pseudorandom generator. This security parameter you can take to just be 128. So it's going to be the product of these two things raised to some constant that no one's worked out yet. I can safely say that the constant's greater than 5, say, and I think it's actually much larger. But in any case, even if the constant was 5, this is a pretty big polynomial. Our witness PRF construction, if you open things up, go through our reduction, is quite a bit better. The level of multilinearity is just the number of users times a linear factor, which works out to be 8 times the security parameter, plus some lower order terms. So we've really made things now linear rather than quintic or even worse. So this is still much worse than the basic protocol, and there's still a lot of room for improvement. But we've made significant progress over the obfuscation protocol, and we also have no trusted setup, no setup at all. So I've spent a lot of my time in the last few years trying to, as I mentioned before, come up with new cool applications of cryptography. Usually this is done through obfuscation. But then I've also tried to remove obfuscation from those constructions and build them directly, say, from multilinear maps. And the resulting protocols tend to be a lot more efficient. One I want to highlight is order revealing encryption, which is basically a fancy encryption scheme that lets other users perform binary search on encrypted data or sorting on encrypted data. And it was folklore that you could do this from obfuscation. But the resulting protocol, because it goes through obfuscation, is going to be horribly inefficient. We actually give a protocol straight from multilinear maps that is implementable. You could go out tomorrow and implement this with known implementations of multilinear maps. And this is really the only application of obfuscation I'm aware of that is implementable. It's still not incredibly practical, but we've made tremendous progress. And I think in the not too distant future, this might actually be something that people would want to use. All right, but there's still a lot of work to be done. And just generally, theoretically, we have all these great applications of cryptography. Everything, running times and parameter sizes, they're polynomial, which theoreticians take to mean efficient. But in terms of practice, we're really quite far from these things being implemented. So one of my goals is to bring these protocols closer to practice. One strategy might be to use some lattice-based crypto to try to implement these things. A natural candidate would be the learning with errors problem. Another strategy might be to come up with more efficient multilinear maps to replace these constructions with. I'm also interested in experimenting with implementation and seeing exactly which of these protocols we can currently implement and maybe try to actually make them a lot more practical. And then lastly, the security of obfuscation and these multilinear maps is not really that well understood. They're very new objects. There hasn't really been an extensive cryptanalysis of them. And I want to get a better understanding of the security for these. All right, so I just want to spend the last couple minutes talking about another research project of mine. This is quantum cryptography. All right, so it's well known, it's been well established that quantum computers, should they ever exist, can break a lot of the crypto that we use today. And the usual scenario is, imagine tomorrow the NSA comes up with a quantum computer, and now they're going to try to break into my laptop and read all my emails. Well, my laptop is still a classical machine, and so the adversary, or the NSA, he's still limited to interfacing with the laptop over a classical channel. And this is really the security model that is normally considered when we talk about quantum attacks on classical crypto. So when quantum computers first come around, my laptop might be a regular old classical computer, but someday I think my laptop will be a quantum computer, my cell phone will be a quantum computer, my refrigerator will be a quantum computer, everything in life will be a quantum computer. And now there's still a good reason, even if we all have quantum computers, to run classical crypto systems. But now the problem is that the adversary, he has a quantum computer, I have a quantum computer. Maybe there's some physical way that he can take advantage of the fact that I'm running a quantum device and actually attack the system over a quantum channel. And even if you don't want a quantum computer, you can just think of the fact that our classical computers, our processor feature sizes are getting so small, we have to consider quantum effects in the computers. And there might be some way an adversary with a quantum computer can leverage these quantum effects to attack our scheme. So we've basically gone through and reproduced a lot of the foundations of cryptography with protocols that can be secure even in this setting where the quantum adversary has quantum interaction with the protocol. So we've done things like pseudorandom functions, message authentication codes, signatures, and encryption. And the obvious future direction for this work is, now that we've done the foundations, can we replicate more of the more recent protocols, obfuscation, multilinear maps, multiparty key exchange, what have you. All right, so that's all I have for you. Thank you very much.
So from a practical point of view, there's still a big gap from the lower left of your diagram to the upper right. Sort of what are the prospects in terms of how we'll see those Wild West things coming into practice in the middle? Are they on the horizon soon?
I think so. So one of the things that I had in the Wild West bubble is what's called multiparty computation. And so multiparty computation, the goal is for a bunch of individuals to get together and compute some function of their inputs without actually revealing their inputs. And we've actually seen a lot of progress. When these protocols were first described back in the 80s, they were incredibly inefficient as well. But now they're getting to the point where you can actually use these things. So that's one place where we've seen improvement in sort of the middle ground, and it's actually becoming practical.
Okay, well, let's thank Mark again.
Thank you.